So going from this to this, I think the important way to think about this is to actually draw this in a slightly different way. So remember that what was happening from here is that this was just nucleophilic acyl substitution on this molecule here. And so if we draw this like this, and then you ask, this is a base, what is the most acidic hydrogen here? You can pretty readily see why you would remove a hydrogen at this position. Right, and so remember, the reason this is drawn as such is that these two molecules are the same molecule, sans the formal negative charge that I've formed after treating with a base. But this is, as drawn here, this is just the enol form of this carbonyl such that it can maintain conjugation. Alright, but if you then treat this with a base, that actually extends conjugation. So then you treat this with ethyl vinyl ketone. So vinyl ketone, ethyl, so ethyl vinyl ketone, conjugate addition, okay, tetrahedral intermediate collapses to give you that, right? These two carbons become these two carbons, carbonyl, same carbonyl, ethyl group, ethyl group. Alright, we went over this step in class. So what is this? So if you imagine the ethyl group, so potassium hydroxide, this should hopefully look pretty familiar to you. So this is, you're forming a bond between this carbon and this carbon. Right, so this is going from here to here as an aldol condensation. From here to here. Osmium tetroxide is a reagent that was covered in a book chapter that we went over, but we did not go through it in great detail. The main thing that happens with osmium tetroxide is that you take a molecule, you take a double bond, and then you add two vicinal hydroxyl groups on. So osmium tetroxide, along with several other reagents, are called cis hydroxylation reagents. So they're both on the same side. The stereochemistry of why it goes to this side is directed by this methyl group, if you're curious about that. This is acetone. Me2CO. This is a Lewis acid. It's the standard Lewis acid that's used for taking acetone, and then what have you done in this case? So this is a hemiketal. Right, so this was one of the basic reactions that we talked about. So in the chapter from last semester, when we talked about addition to a carbonyl group with loss of the carbonyl functionality, this is the first example that we talked about. So hydrogen gas on palladium, that is a hydrogenation, and this we also talked about in class, is that the question is, so you go from this molecule to this molecule. And so to touch on this one more time, so what is the purpose of doing this? The purpose of doing this is that you now take these two vicinal hydroxyl groups and convert them into this ether linkage, or the ketal linkage. So this is effectively a protecting group for these two hydroxyl groups. And you'll see that this is pretty impervious to all the reaction conditions that are going to follow. So hydrogen on palladium, you're hydrogenating a double bond. The question is, why don't you hydrogenate this double bond and only hydrogenate this double bond? Well, the answer to that is that this double bond has a smaller steric requirement than this double bond. This is a tetra-substituted double bond. This is a di-substituted double bond. This is a di-substitute double bond. This is inherently going to be less reactive because of the steric requirements and the substitution requirements. So then you're going from here to here. I'm actually not going to spend very much time on this reaction because it's analogous to what happened up here. So the first step is you generate a formal negative charge here, and that undergoes nucleophilic acyl substitution with this same molecule up here. Sorry. So this is the exact same step. So this step right here is the exact same step as step 1 right here. And so the product out of this would be something that looks like this. And then what you're going to do here is you are going to form this. That, if you form an imine, will actually form an enamine, right? So so the first step does this. The second step is enamine formation. Okay. And remember that this enamine right here, so this is like that. Remember, this enamine then becomes a nucleophile. So then this position right here will become nucleophilic from that enamine. And then what you're doing in this case is adding to this electrophile. So I'll continue this in the next video. I need to stop because of the size.